Hello. Hello and welcome to United Astronomy Clubs of New Jersey. We're back on site for our second to last public night of the season where we will be on site here in Jenny Jump State Forest in Hope, New Jersey. Much thanks to the state park for letting us be here and joining us. So, while people are still filing in and whatnot, as you can see, we're actually inside today. We decided it's a little bit brisk out, so we are indoors at the observatory today, which is a nice change. So while they're waiting, I do want to encourage everyone to join us and check us out at uacnj.org. That's where you're going to find a list of all our upcoming talks and events that we have, as well as links to what type of telescopes we have and information about our member clubs, because yes, we are actually a club made up of other astronomy clubs, because our goal is to actually bring astronomy and science to as many people as we possibly can. In addition, you can also check us out on our social media. That is our Facebook, our Instagram. We have a Discord channel for you to join. Always hit us up with those questions. We do live stream these on not only YouTube, but on Twitch. So if you can't ever make it here, but want to check out our presentation, join us there in the live chat. I know we have a couple of chatters online as we speak. You can also, if you're like, man, I wish I didn't miss that presentation, you can actually go back on our YouTube and also check out past presentations there. And if you happen to have any questions on those, even though the live question and comment section has passed, always put those down in the comment section and we will answer them as soon as we can see it. That being said, always hit those like and subscribe buttons. Just let us know that we are doing good things and you want to see more. All right, so tonight's presentation is Bang, Woosh, Zoom with Paul Fischer. Paul has a Bachelor of Engineering in Chemical Engineering from Stevens Institute of Technology and has worked in the environmental and chemical industries. Though always interested in celestial objects, Paul's official start in amateur astronomy was one night several years ago, lying in an awkward position on his roof in the freezing cold. Of course, holding a pair of binoculars, he did catch a brief, clear glimpse of the Galilean moons of Jupiter and was hooked. After some introductory reading, he purchased his first telescope and is now an active member at Northwest Jersey Amateur Astronomers and volunteers here at United Astronomy Clubs of New Jersey and is actually currently our president. He still manages to find himself frequently outside at night, still in awkward positions, still in the freezing cold, seeing neat stuff in the night sky, and also giving lectures here. With that, Paul.
Thank you, Kim. Hello, everybody. Maybe somebody could chase down our public on site who seem to be delayed at the moment. But let me switch over here from our introductory slides to my presentation tonight. It is called Bang Woosh Zoom. And here I am starting it up from the beginning. And yeah, looks good. Bang Woosh Zoom. I am Paul Fischer, and I am a member of Northwest Jersey Amateur Astronomers and also an observer here. What we call a member is observers here at UACNJ. Let's go to the next slide here, and I will explain a little bit more about Bang Woosh Zoom, why I called my presentation that. But the overall arc of the discussion is this is a discussion of the Big Bang Theory. And specifically, it is a book report, a slightly irreverent book report on the first 3 minutes. So who's to blame for this presentation? Steven Weinberg is the author of the first 3 minutes, A Modern View of the Origin of the Universe. This is an updated version. The publisher's Basic Books, and you can see there the dates that it has been republished. So he gets all the credit for any of the correct information I present tonight. And if there are any mistakes, those are my own. So I will take full responsibility for those. What are we going to cover in the book report tonight? We're going to talk a little bit about the author, a quick review of some of the science concepts. We'll talk about expansion and redshift. We'll talk about the cosmic microwave background. Both the expansion and redshift and the cosmic microwave background are the thrusts of the main arguments for the Big Bang theory. We will talk about a few select moments in time. And then we will have some afterthoughts about the Big Bang Theory at the end. Let's talk a little bit about Steven Weinberg, and just a little note: Steven Weinberg is a PhD. I am reflecting his name the way he had it on his book. So that was his preference, not mine. So he might have been known as Dr. Weinberg, Professor Weinberg. I don't know. I only know that I'm reflecting what I think were his wishes in his, in the publishing of his book. So Steven Weinberg, and he was born May 3rd, 1933, and left us relatively recently on July 23rd, 2021. Here's a picture of Steven Weinberg. The reason chalkboard scribble seems to be ubiquitous for any physicist portrayed in the movies or in the media. So he has the equations on the chalkboard behind him, like you would suggest. However, that is him here. So this is a real life picture, and not some sort of media portrayal of a character. He is also here with fellow Nobel laureates, with Queen Beatrix of the Netherlands. So you're getting the sense that he was maybe a little bit of a, as a Nobel laureate, someone who keeps company with queens, royalty, maybe somebody to listen to, maybe somebody important to understand his career maybe, and why we should listen to him. Here's a very abbreviated list of Steven Weinberg's professional achievements. He had a bachelor's from Cornell University in 1954 and a PhD in physics from Princeton in 57. He had original research and theories in particle physics and physical cosmology. Now, at first blush, maybe particle physics and cosmology or astronomy, what do they have to do with each other? Well, we will just you'll see why those things actually are very crossover very importantly when we're talking about the origin of the universe. He shared the Nobel Prize in Physics with Sheldon Glashow and Abdus Salam in 1979. He had numerous other awards in sciences and for science advocacy. He was a researcher, faculty member, lecturer at Columbia, Berkeley, MIT, Harvard, and the University of Texas at Austin. He wrote 15 books on science and science communication and science philosophy, and he had multiple scholarly and popular articles. So we had a suspicion that he was somebody who was important in the field, and now we know for a fact maybe that he was somebody that we should listen to. Not only that, but we can go ahead at this point and say he was a very accomplished individual and probably the preeminent particle physicist during his time in the field. So a very important person that we should take seriously. All right, to get into the book and to understand some of the things presented, let's review some science concepts, and I promise almost no equations here. It's 100% guaranteed or your money back. Let's review a little bit about particles. Particles that move fast enough when they collide will overcome intranuclear forces and are annihilated. New particles are then creating from the resulting energy. So let's review that real quick. A lot of people think that particle colliders, you collide the particles and then you measure the debris from the collisions. And that, of course, is not at all the case. There is no debris. The particles collide. I shouldn't say no because there is what normally happens, or what happens. I can't say 100% of the time, but what we model to happen is that the particles collide and then they are annihilated completely and turn into completely energy. There are no particles left. A particle's rest energy is given by E equals mc squared. That is equivalency. So mass has an equivalency in energy if you multiply the mass by the speed of light squared. Particles are then created in matter-antimatter pairs from that energy. So particles spontaneously are created in matter-antimatter pairs from the resulting energy. That can even happen anytime. With vacuum pressure. However, in this case, there's plenty of energy to go around, so these particles hang around for a while because they are created from non-borrowed energy, so to speak. The photon, we will also remember, is a particle with zero mass. It mediates the electromagnetic force, for example, visible light. Electrons are leptons and are small with small mass. Photons and neutrons are baryons made up of quarks. They are larger and more massive than electrons. And neutrinos are also leptons. However, they react very weakly with baryonic matter. In fact, you could put between here and the outside of our solar system, say a light year away, you could put a lead for that entire distance, and the bulk of the neutrinos that would travel from the sun all the way out to the end of our solar system would not be caught by or react with that lead. So they are extremely unreactive. All right, let's remember from physical science here the Young's slit experiment. This is the first slide I'm going to show you here with the idea that particles are weird. Quantum superposition, Schrodinger's cat tend to give us a little cognitive dissonance. In fact, let's talk a little bit about what Schrodinger's cat may have been trying to teach us. Schrodinger's cat, of course, is that you put a cat in a box and you do an experiment on the cat where the cat does not survive. If you don't know the state of the cat, in other words, the box is closed, then you can consider the cat both alive and dead. And that, of course, explains quantum superposition perfectly, right? Because that now makes sense that something could be considered both one state and the other at the same time. Doesn't it? Audience, what do you think? No, it doesn't. And I think that's what the point is, that quantum superposition just does not have a our world, our size world analog. That that particle physics is weird. Particle physics is not something in our experience. It's not something we can relate to easy. So we have to take it into ourselves. Particles just act differently than how we think of how they should act in well, I'm going to call it the real world, but let's call it the big world. All right, so that's particle physics, those brief facts. Let's talk a little bit about light. This is light of as seen through a gas of some sort. This gas here is, if you can see, the electrons in the various atoms or ions in that gas absorbed various lights at different frequencies, and this is the case of that whatever that gas was, not moving anywhere compared to the light. However, if we move that light away from us, you see the same pattern. In other words, the same lines exist, however they shifted to the right here on this, and that's called redshift. You can see they moved over to the right a little bit. And here on the bottom one, same pattern again, so it's the same gas, same light source, but this time it was this gas was moving towards us, so we call that blue shifted. So that is redshift and blue shift in a nutshell. Light can behave, with those two, with the Young's experiment here and the redshift here, we can talk about these things about light. Light can behave both like particles and waves. Light from objects in space can be collected and analyzed. Their spectra and apparent luminosities can be directly measured. Similar to sound waves, light is subject to the Doppler effect from relative motion. Remember the Doppler effect? As the train passes by us, it goes, right? That's the Doppler effect. The same thing happens to light. Redshifted light is lower frequency, longer wavelength from objects moving away from the observer and is less energetic. Blue shifted light is higher frequency, shorter wavelength from objects moving towards the observer. So blue shift means coming towards us, red shift means going away. Visible light is a small piece of the entire electromagnetic spectrum. It goes all the way from gamma rays to radio waves. The fastest anything, including light, can travel through space, and you'll notice here that through is, I highlighted through there, in a vacuum is C equals about 300 million meter per second, or approximately 671 million miles per hour. All right, so let's talk a little bit more about the expansion of the universe, expansion in redshift. As we've reviewed those science concepts, let's talk about these. What are these? Who can, in our audience, tell me? Yes, sir. Those are galaxies. Very good. Excellent. And these galaxies and these galaxies here, I took here with my telescope and my camera here at UACNJ. So these are galaxies. This is an interesting galaxy, especially this year. This is the Pinwheel Galaxy, M101. And if you, this is a picture, this picture I took first, and this picture I took a little bit later in April. And if you'll notice, this one, it's rotated a little bit. This one's, say, rotated a little bit to the right. Excuse me, let me make sure I got the, to the left. So the bottom one is rotated counterclockwise a little bit from this one here, just so I could fit them both on the screen there. And you'll notice this dim spot corresponds to this dim spot, but this spot doesn't have an analog here. All the other stars are the same. That star's here, it's right there, the center. This one here, it's rotated a little bit, like I said, but they're there. But this one is here, and this one, but it's not here in this picture. What is this, do you think? The Pinwheel Galaxy, and it happened a little bit earlier. I'd be really impressed. But I'm going to tell you now what this is here. In this galaxy, there happened to be a supernova that a gentleman discovered earlier this year, and that supernova is right here. So it wasn't here in this picture when I originally took a picture of the galaxy, and here it is now. Kind of cool, right? A supernova. All right, but when you want to understand science, you need to understand a little bit about science history and what we started knowing when. So in 1750, first of all, we didn't always know what galaxies were. Sometimes we just thought the sky was the sky and everything up there is just up there, part of maybe our own galaxy or part of what we thought was they called it the firmament, part of the firmament. In 1750, though, Thomas Wright proposed that the Milky Way was a flat slab of stars in which our solar system resides. So our first understanding of that maybe it was a galaxy. In 1775, Immanuel Kant proposed that some of the nebulae that we see, that astronomers observe, are actually circular disks like the Milky Way. So all the way back in 1775, we already started thinking about galaxies. Though widely accepted, Kant's ideas of a universe full of galaxies was debated for the next 150 years. Sometimes we get impatient when scientists don't have the answers immediately nowadays, right? Imagine waiting 150 years for confirmation that galaxies existed. Yet that's what happened in our history. In 1923, Edwin Hubble, you might recognize Hubble's name due to the Hubble telescope. Edwin Hubble observed that Cepheid variable stars in Andromeda. He observed Cepheid variable stars in Andromeda, and using previous work from Henrietta Swan Leavitt and Harlow Shapley, proved that Andromeda was its own separate galaxy and not a nebula in our Milky Way. Now we had proof that galaxies were real. Hubble's original estimate of how far away Andromeda was from us was 1 million light years, but our modern estimate of how far away Andromeda Galaxy is about 2 million light years. And that's a million light years, and that might seem that that's a huge difference. However, he was within an order of magnitude. In fact, it was only twice as far as he thought. That's actually a pretty darn good estimate for 1775, so to be commended. Now, what does that mean? So astronomers weren't sitting around waiting for the galaxy's existence to be confirmed. Since the mid-19th century, which is the 1800s, And among many other things, astronomers had been measuring spectral shifts of astronomical objects, including the previously suspected, now confirmed galaxies. In other words, they knew about that redshift phenomenon that we just talked about, and they started pointing their telescopes at things and measuring the redshift. It was quickly noticed that, with only a few exceptions, all galaxies were redshifted. Hubble announced in but by the way, we just talked about the Andromeda Galaxy. Guess which one of the galaxies is not redshifted, but is in fact blue shifted? Well, since we live on Earth, we can't measure its shift compared to other. But I was just mentioning the Andromeda Galaxy. So you've heard of the Andromeda Galaxy? Yes. Well, the Andromeda Galaxy is actually blue shifted. And if red shifted means it's going away from us, remember what I said about blue shifted? Blue shifted means it's coming toward us. So Andromeda Galaxy is coming toward us. Hubble announced in 1929 that he discovered the redshifts of galaxies in all observed directions increase roughly in proportion to their distance from us. This became known as Hubble's law and is the currently accepted thought on the value of Hubble's constant is between 67 and 77 kilometers per second per megaparsec, which you don't have to remember. You just have to remember that everything in the universe seems to be moving away from us with only a few exceptions. The stars in our galaxy are all rotating around the center of the galaxy, so they can be or don't have to be moving away from us. They're moving up and down, sort of like a merry-go-round, if you think about it like that. Okay? Here is Hubble's plot, Hubble's actual plot, and so what it's saying is the further the galaxy is away from us, the further it is redshifted, and the faster it's moving away from us. What's the implications of his findings? The universe is not static, it is currently expanding. The universe is homogeneous and isotropic. It's called the cosmological principle. And don't worry about what homogeneous and isotropic necessarily mean. You can look them up if you want. It just means that everywhere we look, it's kind of the same thing. Just so you know, the cosmological principle sort of implies that everything is moving away from us. Everything is moving away from everything else on the grand scale, and it's important because physics likes what's called symmetry. So the same thing is true everywhere in the universe. And so what does those two things mean? We can now play with the universe's time coordinates. Since everything is moving away from us, that means in the future everything will be farther away, and it means in the past everything was closer together. So in our mind, we can play with time, and we can fast forward it to figure out what's going to happen in the future. And very importantly for the Big Bang Theory, we can rewind it and know or predict about what state it came from in the past. Dr. Weinberg talks about the future of the universe. He introduced Friedman's critical density and wrote some about the universe's fate, but we will not be talking too much about it here in the Big Bang talk because we're interested in hitting the rewind button. And if you hit the rewind button hard and long enough, almost all the way back to the beginning of time, you will see that things must have been a lot closer together than they are now. So what's the implications of the implication? So when I said they were a lot closer, I mean not just a lot closer, but a lot closer. You really don't understand really, really, really close. Not normal close, but weird close. particle physics close. So this is why when they say that we are conducting particle physics at CERN to understand where the universe came from, this is why it's important. And from an infinitesimal and hypothetical point before particle physics close is when maybe it all started. We now call this theory the Big Bang Theory. Okay, so that was the first rewinding time to a expanding universe back to when it was really close. Seems like a pretty simple concept. All right, so what's the second very important argument in the Big Bang Theory? The cosmic microwave background. Did you know that theoretical physicists predicted the CMB over 10 years before its discovery? So the CMB just did not drop out of the sky, literally. It was postulated from exploring particle physics of the early universe. However, they did not predict its importance as corroborating evidence of the Big Bang Theory. So experimental verification lagged behind its actual proposed theory, its actual discovery. However, these two gentlemen in New Jersey, Homedale, and in fact, discovered the cosmic microwave background. So Wilson is the gentleman on the left, and Penzias is on the right. The CMB's discovery in 1964, Arno Penzias and Robert Wilson worked for Bell Labs in Homedale. They were commissioning a radio telescope for a survey of the Milky Way. They were troubleshooting sources of noise in the signal from the receiving system. They were measuring in the microwave wavelength at 7.35 centimeters. They found a stubborn source of noise that depended on where they pointed the equipment, that did not depend where they pointed the equipment or the time of day. So it was ubiquitous everywhere they pointed their device. And anyone who's commissioned anything knows that you have these stubborn issues when they start up. So they were looking this one stubborn issue that they couldn't make go away. They were trying to eliminate it. This signal happens to correspond to the excitation of electrons in a closed thermal system at a temperature of 3.5 degrees Kelvin. This is referenced as a black body temperature. At this point, the theoretical physicists had this calculation and knew of the possible existence of this signal. However, the experimental gentleman out in Homedale had no clue of its existence. However, through colleagues, Penzias and Wilson were put in contact with the physicists of Princeton who had theories about leftover radiation from the early universe and who were setting up their own experiments. Peebles, Dick, Roll, and Wilkinson. Penzias and Wilson ended up, after conversations, they agreed that Penzias and Wilson had found this theorized leftover radiation, and Penzias and Wilson won the 1978 Nobel Prize for Physics for their discovery. I believe some of the gentlemen from Princeton later, for different contributions, also won Nobel Prizes. In the CMB's discovery in whoops, what's going on here? I'm hitting the wrong button is what's going on. But what is the CMB? What is the cosmic microwave background? After the Big Bang, the expanding universe was very hot, very dense, soup of radiation and elementary particles. Matter did not exist as it does now. It couldn't. It was too hot, too dense, too much energy. Even though the universe was expanding rapidly, the mean free time between radiation particle interactions was unimaginably fast. In other words, the particles were so dense and so energetic that light traveled from particle to particle and could not travel freely. Radiation couldn't go anywhere. The universe was opaque. The radiation and particles were in thermal equilibrium and behaved like a black body. The universe eventually cooled in thermal equilibrium until it reached around 3,000 degrees Kelvin. The electrons then bound to atomic nuclei and regular matter formed. Once that regular matter formed, the universe's density dropped and the universe became transparent. The radiation was released. The universe continued to expand. The wavelength of the light expanded with the rest of the universe and is redshifted. It therefore cooled. That is the black body radiation we now see at 2.725 degrees Kelvin. That is the cosmic microwave background. That is the light from the Big Bang. We can see the Big Bang today. Why do I keep saying black body? So not only do we know that that signal exists, but it's the predicted shape of the curve from a black body. We theorized, or the physicists, we as humanity, not myself, I had nothing to do with it, but the physicists of that time had predicted that it would be, it would have the shape, curve shape of a black body, the various emissions coming at that signal, and because of the unique opaqueness of the universe, and then the sudden release into transparency, and this is an actual plot of the cosmic microwave background, which is in a Planck distribution, and poetically but almost literally, the CMB is the smoking gun of the Big Bang. Again, we can see it. It's at the correct signal level, and not only that, it has the correct shape for the theory that that light would have the characteristic of a black body. That's it right there. I picked this particular, it's a log plot. I picked this particular one because it does show on this plot Penzias and Wilson's, the axes, in other words, go far enough to show here at 4.3 gigahertz, 1, 2, 3, 2, 3, 4, right in there somewhere was where Penzias and Wilson originally found the signal. And here is, we have since attempted to map the cosmic microwave background all around us, and this is a plot of what we found. So it's all the way around us, coming from everywhere in the universe, again, as predicted. So those are the two main thrusts of why the Big Bang Theory. We can still see the light from the Big Bang. We can play with the time coordinates. We know that stuff was a lot closer together at the beginning of the universe and will be a lot further away from us at the end. And so we just ticked the clock backwards in our minds and figured out that things just had to be really close together at one point. So the next step is to talk a little bit about why particle physics is important in these in these thoughts about the Big Bang and what role they played, and then a little bit about what may be happening, some of the afterthoughts, what might be happening maybe at the end of the life of the universe, and some of the other ramifications. So let's talk about what happened in the first 3 minutes of the life of the universe. A few ticks of the cosmic clock, a play. Lights up. We start somewhere very soon after the Big Bang. The temperature is about 100 billion Kelvin. The universe is a soup of matter and radiation and is in a state of thermal equilibrium. The only matter that exists are the electron, the positron, the neutrinos and antineutrinos, and the photon. The density of the universe is approximately 3.8 billion times that of liquid water. Tick. 0.11 seconds have elapsed since the beginning of the universe. The temperature is 330 billion Kelvin. The universe is a soup of matter and radiation and is in a state of thermal equilibrium. The only matter that exists are the electron, positron, neutrinos, and antineutrinos, and the photon. Free neutrons and protons are beginning to form, but then blasted out of existence. Their ratios differentiate: 38% neutrons and 62% protons. That's important. The density of the universe is now approximately 30 million times that of liquid water. Tick. More than a full second has elapsed. The temperature is 10 billion degrees Kelvin. It's going down, we can see. The universe is a soup of matter and radiation, and it is in a state of thermal equilibrium. The universe becomes transparent to neutrinos. That's not the cosmic microwave background. That is neutrinos. And remember, neutrinos don't interact very well with matter at all. So it makes sense that they escaped first. And I have that also highlighted. We will come back to that later. Free neutrons and protons are formed and blasted out of existence. Their ratios differentiate: 24% neutrons and 76% protons. The density of the universe is now only approximately 380,000 times that of liquid water. So really getting thin there now, right? Tick. 13.82 seconds have elapsed. The temperature is 3 billion degrees Kelvin. Electrons and positrons now are stable at this temperature, and they begin to annihilate each other. Neutrinos, previously freed, are cooler than the rest of the universe. The balance of neutrons to protons is now 17% to 83%. Some stable nuclei of atoms, can form. Helium and atomic weights above are still suppressed. Tick. 3 minutes and 2 seconds have now elapsed. The temperature is 1 billion degrees Kelvin. Electrons and positrons are mostly gone. They've annihilated each other. The universe now mostly consists of photons, neutrinos, and antineutrinos. And just note here, I said electrons and positrons are mostly gone. We will come back to that again in our afterthoughts. The balance of neutrons to protons is now 14% to 86%. Some stable nuclei can form. Helium nuclei can form now, but are suppressed because deuterium, a necessary precursor to forming a helium nuclei, is still not stable. Brief intermission here at 3 minutes and 46 seconds have passed. A lot of stuff has happened already in 3 minutes and 46 seconds. Deuterium nuclei, however, are now stable. This is important because helium nuclei now can form at a rate twice that of available neutrons in the universe. 13% neutrons to 87% protons. Does anyone knowing the makeup of most atoms in the universe know why these numbers here are important? The temperature is now about 900 million degrees K. By the way, it's because we now know that helium and hydrogen form most of what's in the universe at something like these ratios. 34 minutes and 40 seconds have now elapsed. Okay, we just let's go back here. The book, remember, was called The First 3 Minutes. We have now that was our 3-minute mark. We have now gone slightly past here at 3 minutes and 46 seconds, and we're now talking about what happened after the first 3 minutes. So 34 minutes of everything in the universe. 34 minutes. It was the first 34 minutes ever. 40 seconds have elapsed. The temperature is 300 million degrees K. Electrons and positrons are gone, except for one part in 100 million. Nuclear processes have stopped. Nuclear particles are bound in mostly hydrogen or helium nuclei. In other words, we now have our hydrogen to helium concentration that we now observe even today in the universe. It's still too hot to form stable atoms, and the density of the universe is approximately 9.9% of liquid water. And as the lights begin to fade on our play, our 3-minute play, not much interesting happens for 700,000 years. The temperature drops below 3,000 K, though. Stable atoms are now possible. Free electrons and atomic nuclei begin to pair up to make happy little atoms. The universe now becomes transparent to radiation, and so the cosmic microwave background is released. Stars and galaxies begin to form, and another 10 billion years or so goodbye, and Dr. Weinberg writes the book, The First 3 Minutes. So let's talk a little. That is our play. You can see there was a lot of calculations, understanding of particle physics required to understand those temperatures, what was happening at those temperatures, what was available, what had too much energy to form, what could form at those energies, that type of stuff. So that was us understanding. So particle physics has a major role in understanding the earliest parts of our existence as a universe. Afterthoughts, things to think about. The cosmic neutrino background, as predicted, 1.75 degrees Kelvin. So we mentioned, and I highlighted it, that the neutrinos were released first and started to cool earlier than the rest of the universe. Well, we found the cosmic neutrino background. We've had had a lot of experimental physics has gone into capturing and measuring neutrinos. So this one took us longer than discovering the cosmic microwave background. But we did find it, and it is cooler, as expected, at 1.75 degrees Kelvin. Cosmic inflation and the cosmic microwave background. Just wanted to mention about cosmic inflation. Has a very interesting thing. Remember, the other highlight I had way back in the beginning of our talk today was that things can only travel at our cosmic speed limit of 300 million meters per second. However, cosmic inflation happened faster than the speed of light. And why is that not a contradiction? Because this was space expanding It wasn't anything about anything traveling through space. So space expanding itself has nothing to do with stuff traveling through space. So therefore, the speed of light speed limit does not apply to the inflation of the universe. Before the Big Bang, well, we just don't have physics to describe what happened before the Big Bang. So that is a big question mark. Different people have different spitball theories. However, we don't have physics to describe that state. So the best science can say is, we don't know, maybe it was something like this. Or we don't know, maybe it never was maybe there was never an actual beginning, but just a huge inflation, or many other theories. There's just no concrete evidence to point to one thing or another. I talked about the fact that most of the electrons not in matter antimatter pairs annihilated each other. Not all of them. Electrons, the negative, won out. There were more electrons for some reason than positrons, and so therefore we have a universe consisting of electrons and atomic nuclei, and not their antimatter equivalents or pairs, and that's just the way it worked out. But why that happened is still a big question in physics. Dark matter and dark energy, of course, are newer ideas, and Dr. Weinberg did discuss them a little bit. There's still a lot to discover about those two phenomena. And finally, we concentrated on rewinding the clock, but not fast forwarding the clock. The heat death of the universe is one of the more popular theories, where the universe just continues on for trillions of years and things get further and further apart, less and less energetic. We just lose enough energy to do anything meaningful anymore, and so the universe goes out with a quiet whimper, so to speak, trillions of years from now. This is the current cosmological model having to do with the Big Bang. Dr. Weinberg did update his the first 3 minutes several times. However, you'll notice that although the inflation and the afterglow of light pattern and the Big Bang expansion, inflation and expansion all still exists as described by Dr. Weinberg, some of the timeline are different in our current understanding. That's just refined science over the period of time since Dr. Weinberg was active. So it's just new information, new timings, new values. However, the whole entirety of the theory as he presented it remains the same. And just finally, since the James Webb Space Telescope went up into the sky, there's been some people claiming, didn't the James Webb Space Telescope break the Big Bang Theory? And the answer is no, just no. There are some people who have had it in for the Big Bang Theory for a while, and they've of course, when the James Webb Telescope new data came out, they jumped on it immediately. However, there was some, not controversy, but some scientists detected an anomaly in the data. There was early identification of results relating to the size of early galaxies, that they thought the early galaxies were bigger than expected. The mistake, there was a mistake though, and it had to do with the light extinction and the application of two different methods of understanding redshift of galaxies. One was a photometric method, the other a spectroscopic method. The photometric method was originally used. However, people came behind the photometric application and used spectroscopic redshift measurements, and the size of the galaxies using the spectroscopic method agree with our understanding of how big galaxies should have been in their original formation. So it jives well with theory and the idea that the photometric method does not sufficiently take into account, or the light extinction. The photometric method is very sensitive to light extinction, which means light can be absorbed by things between us and what we're measuring. That was the light extinction was not accounted for as well enough for the photometric method to be viable. Current estimates of early galaxies do fit the CDM model of galaxy formation. And just as I mentioned, some people jumped on this maybe a little bit early. Things, anomalous things happening in data happens all the time. That's how we learn things. That's how we understand that maybe the photometric method does not work in over these huge distances as well as the spectroscopic redshift method. So we did maybe learn from that experience, and that happens in science all the time. So jumping on anomalies is silly because that's how we learn things. So to help combat maybe with motivated reasoning and to prevent keeping an open mind and to prevent a little bit of motivated reasoning, I suggest these two sources. On Bull Stuff by Harry Frankfurt, that is a philosophical paper, and Skeptic's Guide to the Universe by Dr. Stephen Novella and others. That's a podcast. Maybe give those a little bit listen and understand a little bit, or read them and get a little bit of understanding about motivated reasoning and why one shouldn't necessarily jump on things right away like that. All right, and finally, I'd like to thank everybody and to remind them to join an astronomy club and to stay safe. And I don't know that we have anything here on site live to show anyone, but wherever you are, enjoy your evening. Thanks.
All right. Thank you, Paul. And thank you, everyone who's come out. So, we are going to be having a question and answer session. And because we're indoors, I can actually kind of see a little bit because we have more light than outdoors. Yay, I'm not completely night blind inside, just outside. So, first things first, we are using our headlights when we go to leave because I don't want to get run over, and I bet you feel the same way. It is not the night for that. At the same time, if we have any flashlights, we do keep them pointed towards the ground. Again, do check us out on our website, uacnj.org, and our social media presence, Facebook, Instagram, and our Discord. So, for our first, I'm going to start us off with an online question. And I'm going to actually treat these two questions as one. Paul, but what if you got something right and he didn't? You could have had a breakthrough scientific discovery or thinking and not even realized it.
I very much doubt that. Being not only a giant in his field, at one point he was the preeminent. So one of the rare brains in the entire history of human beings. So I highly doubt that between Dr. Weinberg and myself, that I would be the one who's right and he be the one that's wrong. We'll keep that as a nice theoretical, but for a practical purpose, that's just not happening.
No faith in oneself. Any questions out here? All right, so our next online question is how many how much scientific mastery do you need to gain before you start being desirable for royals to be seen in public with you?
Uh, can you repeat that question again? I don't know
So,
whether I necessarily followed.
f- from what I think they're saying is how advanced in the scientific field or prominent in the science field before royals are like, yeah, I can be seen in a photo with them. I can be seen out in public.
I imagine as any other human being, some of the scientists, I'm sure, are either socially oriented or not, and so that I imagine depends upon the individual. But the fact that Dr. Weinberg spent time with science communication and lecturing for as long as he did. And I think I would say that he probably enjoyed teaching people and speaking about his expertise. So I would say that I would say he was probably a very approachable guy.
Yeah, but how how he could have been the most approachable. I think the question was he could have been the most approachable guy in the world, but at what point do you become someone that a royal was? Yeah, let's have a picture of us shaking hands.
Yeah, I think
I
I
think
think
there's
Nobel
a
Prize
limit
laureate is
there.
probably a good bar to judge that with. However, there are very many notable scientific people that I'm sure have similar experience.
All right, so our next online question. What is science philosophy? Is that like the ethics and morality courses you have to take in college?
Um, so science philosophy, for instance, the scientific method is a very important part of science philosophy. So one could, if you go, you've heard people say doing meta thought or going meta with something. It's the thinking behind the thinking. So that would be what science philosophy is. How do we do things? What makes them robust? How we can pursue truth with these things? So the bigger questions in maybe science methodology and what science is trying to achieve. So I've never studied science philosophy, but I have to imagine that I've heard as the scientific method as being part of science philosophy before. So the scientific method and some of the meta thinking behind science.
All right, questions. All right, so our next online question is referring to the two pictures that you took of M101. Why are they both slightly different colors?
Uh,
Does that have to do with the data, the processing, or the environment the data was taken in?
Well, I'm a beginner. I'm not even what would be considered an astrophotographer. I do EAA, so my processing needs a lot to be desired. Also, they were done. They were done with the same camera and the same capture software, but were not done with the same telescopes. So I want that night. I was with the second telescope. I was just checking my setup with a different scope, one of the club scopes, in fact. And I've since connected to that scope several times throughout the season as the weather has agreed with us. But
The very rare
the
chance
very
this
rare occasion
season
that it has
is.
agreed with us. So that was the main purpose of what I was doing that night. So you might be detecting difference in how I processed it, but also just a difference in the equipment used.
All right. Next question. Is the Hubble telescope just named after Edwin Hubble, or did he have a hand in getting it up there?
I don't remember the name of. It was somebody who went on. I forget who it was. Somebody who went on a multi-decade campaign to get a space telescope, but I don't think it was Edwin Hubble. I think it was named after Edwin Hubble. However, the project manager who drove the project and campaigned and lobbied for it with our government and campaigned for it was a different gentleman, and unfortunately, off the top of my head, I do not remember his name.
This is why when people make scientific discoveries, they push so hard to get it named after them so that you don't forget their name.
Don't take me. Look that up for yourself. I don't want to. If it was Edwin Hubble, I don't want to steer you wrong and say that for certain. But I think I remember that it was two different people.
All right. This one's more of a smart aleck comment. Uh, you started sounding like an ad for fancy water there when you were going like isotropic. Is the universe also alkaline and refreshing like smart water?
Yes, the terminology can get thick and vague, at least to our everyday language. But homogeneous meaning the same, and isotropic meaning whatever direction you look. So whatever direction, it's the same. So that's the two words.
All right. And this has to do with the slide you had up was what does black bodies mean? Did they mean black as in light, the light spectrum, which is if you're lacking any light, it's black, or black as in like artist paint where it's you add all the colors together and get black?
Yeah, not exactly either of them. It's a specific scientific definition, meaning that there's no reflective light, there's no spurious light because of that body. So if we look at a planet, for instance, we're seeing a lot, when we see a planet, we're seeing a lot of reflective light off of that planet from the local sun. So that could mess up our calculations if we were trying to do calculations there, because we're getting light from another body, so we can't make any conclusions about whatever's coming from that, whatever light might be being generated by that planet. For instance, Jupiter has some heat processes going on in the middle of it. It's actually generating heat, it's generating light, and we could, if we could filter out our sun's light, make conclusions based on that, but we have to be smart enough to know it's not a black body, and we have to subtract the sun's light, the reflected sun's light, out of Jupiter.
Now I want to know how bright Jupiter would be if you put it like by itself.
I don't think that bright, but I
like
think
like a dim night light in the corner of the kids' room.
I don't know enough about detecting light from Jupiter to comment about that intelligently at all. But I imagine we could detect it or have detected it already. But in the case of a black body, there is no spurious light coming from. It's only the light generated by that source that's coming from that source, and that gives the Planck distribution that I showed you.
All right, questions out here. All right, so our next question is, what is 100 billion Kelvin in Fahrenheit or Celsius?
So Kelvin is it's no, that's Kelvin to Celsius, exactly. So it's minus 273 degrees Kelvin. And I was trying to think Rankine for some reason. Thank you for correcting me. Yeah, 273 is not even a drop. The difference of 273 degrees is not even a drop in the bucket. Correct.
Okay, so for the online people who would not have heard, one of our other observers here, who is also very knowledgeable, said that at the large scale that they're on, Kelvin and Celsius basically reads as might as well be the same thing. We're still out on Fahrenheit, so you could probably Google that and have a fun time thinking, man, must feel like Florida in the summer. Anyhow, our next online question. You mentioned Matter, matter being soup at 11 seconds. Is it chicken noodle, tomato, lobster bisque, maybe a lovely minestrone?
Imagine whatever you will. It's a very high energy particles that at that point had formed, the leptons mostly, and energy. So it's energy and high energy particles, the smallest of the particles. So that's the soup. And if you want to imagine that as chicken noodle, that's a very good choice. Or tomato. I make both of those at home, so either one of those I would find perfectly acceptable if you want to describe it
Actually,
that way.
I think you had said on a later side that things were still later on too hot for things to form solid atoms and whatnot. So I would think it would have to be something like a tomato where it's very uniform,
Remember that let's just
not like
differentiate
chicken.
between atoms and particles. Some of the particles are extremely high energy, the particles that actually go to making up atoms. So atoms did not exist at that point, but relatively quickly after, or actually really quickly after the Big Bang, some particles began to form.
I was just thinking that if you're talking about atoms not being able to hold together, at that point you probably don't have any solid chunks like you
You
would have
don't
in a
have
chicken
you
noodle.
don't you definitely don't have chunks, and things were so dense. This is not a soup that in any way, shape, or form you'd have to
Talk about a meal that's a little too heavy.
you'd have to blow on it for a while for it to cool down enough for you to eat it.
All right, so I am coming down to the last couple of questions here. So if you're online and do have any questions, do get those in. Uh, if we don't see them in time, I will address them when I go back to look at comments later. So, our second to last question here online is: are happy little atoms the science version of the Bob Ross happy little trees?
I guess they could be. If Bob Ross were uh, a particle physicist, we might have been talking about happy little atoms in our everyday lexicon. But thankfully, I think the show, his show, would have been a little less popular than his painting show on Channel 13, but maybe not. Maybe a little too dense for a lot of people to enjoy on 13 during the middle of the day.
I don't know. I'm kind of envisioning some really interesting Bill Nye and Bob Ross crossover
Certainly,
series.
science continues to be a very popular subject, and certainly the Big Bang Theory is a well appreciated and highly debated topic. So certainly that could have been very popular also. But thankfully, Bob Ross gave us many pretty pictures, and I do love a happy little tree myself. Uh, so thank you for that comment.
All right. Any questions here? I don't even hear crickets because we're inside. I just hear the server. All right. So, last question here is: what is beyond space? And I assume this is because you said, space existed and then expanded, which technically implies that there is something, you have space and then not space over here.
You would think that, but that is not true. So everywhere was a lot smaller than it is now, but it was still everywhere. So everywhere is getting bigger, but it was still everywhere when it was a lot smaller. So in other words, we have what is called the known universe, where we can see back in time, because the further one goes back, the longer it takes light to travel to us. We can approach close to the beginning of the universe. However, there's a distance beyond which we cannot see because light has not had the time to travel to us. But I think the most popular, so the best scientists can say for sure is that we don't know what is beyond that limit because there has been not enough time for any data, including light, to have reached us from beyond that point. However, I think the most popular theory is that that is still just a part of everywhere and that the universe continues on isotropic and homogeneous, and it just keeps going.
So that probably means that technically, even as you get out closer to the end, you'll never see the end because you can see
and
that
we
much
can't
farther.
Instantaneously travel to the end, so it would take you time to get there, and so it just still takes that time.
So it's
to
like
get
the
to you.
Minecraft world. You have to wander around, and as you wander, the map expands.
True. Yes, Marcus.
We got a question out here.
There is no end. To use the word end is erroneous because we have no evidence there's an end.
Correct.
Right.
There is, but that's the kick, right? Is
That's
that we
right.
can't say one way or the other because we just don't have the data.
That's right. So if the universe is 13 point something billion years, that is our essentially event horizon. The light has had, that's the furthest object that we would be able to see due to the propagation time of light.
And that's why that envelope is called the known universe.
That's the known universe, but that's not the end, right? So there's the unknown universe where sometime in the future we may see light from it.
And we can say that we think it's like that, as Marcus had just described. However, we don't have any data because we can't have any data from beyond that, so we can't say 100% one way or the other. We can very much think it and say, hey, we think that's really the way it's going to be. But scientists are extremely careful about this. If they don't have the data, they can't say that it's like this because they don't have data. And part of the science philosophy, as we were talking about earlier, is that if your claim is unfalsifiable, then you cannot make the claim. And scientists are very particular about that.
Yeah, I dislike infinities because they're kind of because no matter what you do to an infinity, it's always going to be the answer is going to be infinity.
We can always speculate, and that's why science fiction is so fun and wonderful to read about, is because great creative minds and even scientists themselves enjoy, I'm sure some of them enjoy science fiction quite readily because we do explore those hypotheticals.
All right. So it looks like our online questions have dried up. Last call for questions out here. All right. So I want to thank you, Paul, for another great presentation. I want to thank everyone who's joined us not only here, but online. Do remember to hit those like and subscribe buttons if you're online now, or if you happen to catch us online in the future. Again, website, uacnj.org, and everyone have a good night.
Thank you, everyone.